It's going to talk about field-affected aerosol-assisted chemical vapor deposition of tantalum oxides and oxynitrides. So, give me a minute, I'll get your slides up. And the timer's just here. Green means go. And red means stop.
Very cool. Right, hi everyone, thanks very much. Yeah, time to start the day off with some material science. I'm going to be talking to you about field-affected aerosol-assisted chemical vapor deposition. Quite a mouthful. Going to be looking at, yeah, some tantalum oxide thin film materials mainly to start with, and I'll touch on a couple of the other things I've been looking at as well. This is all work I've done at the University of Bath under Professor Andy Johnson. I've had the luck to be assisted by a couple of nice MChems, Floris and Tom. Is this turned on? So yeah, I mean, what is a tantalum oxide thin film, or really what is any thin film material in general? Well, there's a wide range of applications these can be used for. They tend to be kind of semiconducting materials on the order of hundreds of nanometers to maybe 10 microns thick, used in a wide range of industries from like semiconducting microchips through to batteries or solar panels. The application I'm looking at doing with them is photoelectrochemical water splitting. That's a process where you take your thin film material, drop it into water, shine some sunlight onto it. The sunlight can excite electrons in the thin film material, which drives a catalytic process where the water is split into oxygen and hydrogen. This is a really great thing to do in a green renewable economy because you're making hydrogen from water and sunlight. The way I've been making these thin film materials is by using aerosol-assisted chemical vapor deposition. This is like a technique where I'm taking some inorganic precursor complexes for my thin film materials, dissolving them in an organic solvent, and then I'm transporting them up to the reaction chamber via atomization, aerosolization, under an inert gas flow, moving into a heated reaction chamber. Once there, the solvent evaporates, my precursor complexes are deposited onto a target substrate, and then they're designed to decompose into the thin film material I'm looking for. So what are some examples of some of these materials I've been looking at? I should say as well, tantalum is quite a heavy D block element. It sits below vanadium for people who know anything about chemistry. And basically to make tantalum oxide, I'm trying to cram as much oxygen around a tantalum center as I can, and I want that oxygen to stay there when the materials decompose. So here are some examples of tantalum oxide precursors. So starting from the kind of the ethoxide species on the bottom left, which is a bit too volatile to be used in the deposition process, I've kind of reacted it with a more universal tridentate ligands, moved through to kind of the complex 1 in the middle, which has kind of my ligand with a couple of ethoxides left, showed above as well. This works as a chemical vapor deposition precursor, as I'll show on the next slide, but I can then take it further by reacting this species with water and forming kind of a tantalum oxygen tantalum oxide bridge. You can imagine that's part of the way towards forming like a microscopic tantalum oxide material. In terms of seeing how good these will be for the deposition, I've done something called thermogravimetric analysis. This is a technique where basically I'm heating my samples under an inert atmosphere and seeing how mass is lost, basically how the molecule decomposes into volatile fragments, leaving behind the material that I want. You can see that for my first complex, complex 1, there's kind of 2 decomposition events happening, one around 210 to 20 degrees, another around maybe 310 degrees. So that's great, it proves the complex decomposes. However, it does fall below this black dotted line, which is kind of the target mass if all of the complex was being perfectly converted into tantalum oxides. That indicates that at some point during the process, there's some volatility of my tantalum species occurring. This is being evaporated away and lost. The complex 2, on the other hand, does a bit better. It does once again have a couple of mass loss events. The first one of these is actually just due to some pyridine that was present in a crystal structure I used to crystallize this molecule. The second mass loss event is the more significant one. It does once again fall below the dotted line, but this time about 3/4 of the material is remaining behind, so hopefully more efficient. I went ahead to do some depositions with these. So this is just conventional aerosol-assisted chemical vapor deposition at this point. So I dissolved these precursor complexes, aerosolized them, and passed them into my heated reaction chamber. There's lots of parameters that can be varied here, such as the flow rates. So how much argon I'm flowing through, how much aerosol is being generated, at what size. Concentration, so how much of my precursor complex is dissolved in the solvent. I've been using THF mainly. Process temperature, so how hot the reactor is, and also the substrate, the material you're depositing onto. I've done about 40 different tests across all these different parameters to try and optimize the system. You can see some of the things I've deposited onto, such as fluorine-doped tin oxides, copper, or silicon, and they produce quite varied structures. You can see I've got kind of these either spherical or more cauliflower-like morphology systems happening. Analysis by Raman or a technique called energy dispersive X-ray spectroscopy proved these are tantalum oxide thin films. One thing all these thin films I've made have in common, unfortunately, is they're all rather amorphous. That is a problem that's quite well known with tantalum in general. Despite the fact they look like they have these different structures, really on a crystalline level, everything is still amorphous. I can prove that using powder X-ray diffraction. On the bottom left, I have one where it looks like there might be some crystalline needles coming, and that's quite promising, but it turns out if you analyze them, they're actually just some copper oxide that's been created from depositing on copper. You can see my tantalum particles kind of interspersed through there and not really interacting with that. One consequence of my material being a bit amorphous is that actually raises the band gap. The band gap of these materials is kind of the energy that's required to promote electrons and drive the water splitting process I was talking about. In this case, my band gap is really quite high. It's at about 4.7 electron volts. That's about 265 nanometers, or in the UV range, really too much to be shining sunlight on it to do some water splitting. So this is a target to try and reduce. Now, one way I can try and reduce this is by moving to a different class of materials called tantalum oxynitrides. So this is by introducing some nitrogen into the structure in place of oxygen to make TaON. This is known to have a significant effect on lowering the band gap. It should bring it down to about 2.4 electron volts, 520 nanometers, so more in the visible light range to drive this with sunlight. I've been designing some single source precursors to do this from like a single complex. You can see I have on the bottom left this kind of tantalum imido complex. And on the bottom right, if I just want to introduce a little bit of nitrogen, I have kind of this dimethylamine group, which is stuck on this tantalum oxide species. I have both of these. I've done the thermogravimetric analysis. Of the two, the complex 3 appears more promising because it has the two-step decomposition process. However, the first little line up top is from some toluene decomposition. The second line is the main decomposition of the molecule. Once again, around 3/4 of the mass remains behind, indicating it's appropriate. These are quite experimental molecules. There haven't been too many attempts to synthesize tantalum oxynitride from a single source precursor, so I'm looking to explore on this in the future. On the other hand, there's a second part of my project too, which is investigating fields during the deposition. So like what happens if I apply some electric and magnetic fields? Because these complexes are a bit experimental, I haven't approached that with these just yet, though I'm planning to. So instead, I moved over to a different, better understood class of materials, which is titanium dioxide or titania films. These have been studied since the 1980s conventionally, and they're known to exist in 3 morphologies, kind of anatase, rutile, and brookite. So I can really tell what I'm guessing. I designed a precursor complex bespokely for this, kind of containing these oxo bridges again. It turns out this species I designed by reacting with water actually exists in a monomer-dimer equilibrium. So kind of you can see the double bonds to oxygen on the left being the monomer, on the right you have the dimer. In solution, they equilibrate. You can get the crystal structure in the top right. But both of these fragments have a relatively similar TGA or thermogravimetric analysis. They both decompose to about the target mass I want, indicating they're both suitable to use. So I did some depositions with these, and I found they create anatase, thin films, got kind of an example on the side now. I went ahead and applied some electric fields to this. This is some more recent work I've been doing, and these results are a bit preliminary. You can see that the molecule has kind of a dipole running across it in the top left-hand corner, so all the oxygen sitting more on one side, more electronegative than the nitrogen, so hopefully this molecule should align in the magnetic electric fields. With my setup here, you see I have my heated element from below for the reaction chamber. I have 2 electric field rods running through it. I can use these to make about a 200 kilovolt per meter electric field, which is reasonably high. I've applied this field. Provisionally, I've only done a brief analysis so far across my substrates and found that while the thin films do remain anatase in overall morphology, they do seem to be slightly sharpened by applying the electric field so far. An interesting thing that they do, which I wasn't observing before, was kind of growing these dendritic macro structures. You can see this is now on kind of a 10 micron plus scale. They can be observed with the visible eye, naked eye, some of them. They grow out of the substrate material, try and stretch towards the other electrode. When the electric field is turned off, these do actually collapse and fall back onto the thin film material. Yeah, I've analyzed some of these. You can see them with SCM. I've also done energy dispersive X-ray spectroscopy, proves they're made of titanium. So this is a titanium structure, and it is in fact still annotate. So I haven't managed to change the morphology of my structures just yet. Little side project I was doing as well, looking at some dopants, so introducing cerium or praseodymium to these titanium systems. This is done because while titanium oxide is quite well known, it does suffer the same way tantalum oxide did with having a rather large bands gap and introducing some kind of donor levels by adding like 1 or 5% of these F block elements would be a way to try and lower this further. It also reduces something called recombination, which is like a physical effect that's known during water splitting. So you can see I've tried to incorporate this into my thin film material. This was kind of a MChem project I was working on as well. You have some cerium, seems to sit more homogeneously in the films. I can just about characterize it sitting in there. The praseodymium is quite difficult to characterize when I've done it with that, but I think from the SCM images, which are really quite zoomed in, you can see there's kind of about 10 nanometer or so structures that are present on top of the thin film. It seems to be sitting on the surface rather than being melded together. That's quite difficult to actually characterize, but that's what I believe is happening. So that was just a side project with that. So just to kind of summarize overall, I've mainly been looking at some tantalum oxides and tantalum oxynitride materials. Then I've also done this investigation into titanium oxide, mainly for dopants and investigating my magnetic fields. In the future, I'm looking to focus more on the tantalum oxynitrides because I think they're quite promising for future development. Do some depositions of them, maybe in the presence of the electric fields as well. Also want to look with the F block elements I showed on the previous slide. Can I introduce them together with tantalum oxynitrides? There's quite an interesting emerging class of materials called like perovskite tantalum oxynitrides. An example being the barium tantalum oxynitride, kind of shown in the middle at the bottom. This can be done with F block elements as well. I want to try and introduce them into the structure because they haven't really been investigated yet. Also want to try and do that because the F block elements are paramagnetic. Why do I want paramagnetic elements? Because I'm also interested in investigating what happens when I apply magnetic fields across substrate. You can see on the bottom right-hand corner, I have kind of these large magnetic field solenoids I've designed to pass a magnetic field through my system, and I want to see what happens if I do that, say, with some F block elements. So yeah, thank you very much. Does anyone have any questions?
Anyone have any questions? Right.
So F block elements can be kind of rare on Earth. What are the implications for actual practical water splitting?
Yeah, obviously you'd have to limit the amount you're using into the thin film materials. When I was just using them as dopants, it's not so bad because they're only present in like 1 and 5% quantities. With the F block elements, if they're used more stoichiometrically in the future work I'm looking to move towards, that's more just an experimental thing to see if it can be achieved at all. That's a class of material that hasn't been looked at all yet. It's the barium tantalum oxynitrides have been looked at, but they've been seen to suffer from some stability issues. I just want to see if it's at all possible to do it with the F block elements instead. Hasn't really been looked at, and I think it could be quite interesting.
Oh, sorry, it's great. Behind you. Behind you.
Just wondering what the evidence is about whether the particles decompose in the gas phase and then land, or how
That is a good question. It is, to be honest, not all that well understood, and I think it varies depending on which solvent system you use. I didn't really talk too much about the different solvents that can be used during CVD. I think I was using THF, which perhaps there's some consensus in the group volatilizes away during the vapor phase transport, and then you're depositing the material. On the other hand, with toluene, the deposition seems to happen in more larger nodules, which might imply that if you use toluene, it doesn't evaporate fast enough, and you actually deposit some of that as well. So it's solvent dependent.
Great. Should we give another round of applause for the speaker? is that